First. So hi everyone, thank you very much for coming on time. Really appreciate the 6 of you here. Hey. Okay. That the 6 of you got bonus lah. Okay, plus you. Thank you for coming on time. Yep. Okay, so today we are going to talk about hashing, which is like the fun part of tutorial of 2040 tutorials. So before that, as you've seen in the slide, you can feel free to scan the QR code. Anytime you have questions, feel free to ask here. I will discuss them during the break later lah. Okay. So yep. And before we start, let me do a quick reminder here. Wait, where is it? Okay. So for those of you who may not have known before, so I have like this anonymous feedback form that has been on from the start of the semester. I'll be checking the form every week because I will allocate time to check lah. So if you think that you might have some suggestions for improvement, please feel free to fill in this form. I can try to improve lah, because we still have like about 4 tutorials left. Okay, so best for me to better suit you as a tutor. Okay, so that'll be it for just the checking in part. And without wasting much time, I'll be moving on to the actual topic today. That is about hashing. Okay, so we are going to do a very quick recap on hashing and also how collisions work. So the key idea of hashing is basically you want to try to fit everything in an array, but then if you try to fit everything in an array, right, to search for something, if it's not sorted, then it will take OM time, right? Because you have to traverse through one by one to get the item. But what if it is sorted? The runtime is? If you have a sorted array, say a sorted array of integers, how to find if a number is in the array? Log n, okay? What if we can reduce them into just O1 time? And that is basically hashing. So suppose I have like this one value here, which is just a string value. So I will convert this into a specific integer that is done by your hash function. Okay? So your hash function generates a specific key from your given value. Okay? Now this key, what do? I basically have a table that is just an array. So at index something, I will have like, for example, initially there will be no values at all. So I will place my value as the element at this position. Okay, so this is hashing. Basically what you are doing is, from this thing, you are going to hash it into one specific index, and then you are going to store it in the table corresponding to that index. Okay? So hashing is simply storing data in an array-like structure, but then we want to enable lookup without doing traversal. We don't want to traverse one by one to find the element, but we convert them into an index such that once I hash this to a specific index, I can just look that index in the array. That is what hashing is about. Okay? Why do we do so? Because we want to support this O1 lookup. Okay? We want to support O1 lookup, O1 edit, O1 random access. Okay? And how do we do so? It depends on your hash function. Okay? Your hash will change from some value into a specific index where you can just now look up the index of that array. Okay, so hash changes from a value to an index, then you just look from the index. Okay, that is basically what a hash table is. Now suppose my value is here. Okay, but in this case, okay, it works. But suppose I have like another word, super. When I hash it, it returns the same index. What do I do? Linked list? Okay. So the first way is to do what we call chaining. Okay. So we can store both of these values together in one array. But then how do we store it? Because array has a specific size, right? If we make a fixed size, then we can only store, like, for example, just integers or just strings. So in this case, we are going to instead use a linked list. So we are going to store, instead of the value here, we are going to store a pointer to a linked list. Okay? This will point to a linked list, a node containing value, and then value will later point to a node containing super. And this is called chaining, because you are going to create a chain of values together. Okay? Hence this is called chaining. But the problem is, you are going to spend more storage because of keeping the nodes together. Okay? One node, if everything here will need a node, right, then I will need ON space to store all of the nodes. So it is not really efficient in terms of storage. So what else do we do? I think Monday's lecture. Any other ideas instead of doing a linked list?
Bump the value to the next.
Okay, so we see that the next part here is empty, right? What if I just put the super to the next one? Okay, it looks right. So I see that 33 here is full, so I go to 34. Okay, and then I store my value of super here. This is what we call open addressing. Okay, so you're going to find an open slot in the table, then you insert the value there. Okay, the process of searching for the open slot is what we call probing. So you probe the table for the open slot. There are two types of probing, actually a lot of types, but two common ones that we teach is, first of all, is linear probing. Linear probing means once you see that, oh, there's another value there, you're going to search one by one all the way until you see an open slot. Okay. The other one is called quadratic probing. So quadratic probing is, for example, I go to here. I see that, for example, there's a value here. So I go to +1. But if there's another value here too, I will go to like +4, +9, +16. So the multiple of the next one will increment by a quadratic number. Okay, that's what we call quadratic probing. So far, any questions? Questions? Doubts? No? Okay. Now what about the runtime of hashing? If you see from the previous examples, right, every time you have a collision, if you do a linked list, there might be a possibility that everything will collide there, right? There's a possibility doing so. Or if you do open addressing, like, for example here, you have a value here, and everything below is occupied. Then when you want to find an open slot, you have to go one by one until you reach the top one. Okay? In this case, for hashing, for most collision cases, your worst case runtime is most likely ON. Because there's a possibility that everything else is inside like one bucket, or everything is close together. Once you probe, you will have a chance that you need to traverse through everything. So this is the worst case. But what is the expected runtime? What is the expected runtime for hashing? Expected? O n per m, right? So our expected time is O1 plus n per m. Why is it n per m?
Because you need to
You go through the linked list.
And in average, the linked list have length per m.
In average, the linked list has length n per m. Okay. So here's a bit of a how do I say? A bit of an analogy lah. For example, if your table is only 3, okay, 0, 1, 2, okay? So this one corresponds to 1, 2, then my hash function will be like, from x I will change to modulo 3, okay? So this will be like my hash function. Then if I have like, for example, 100 data points, okay? In the worst case, I might have all of my 100 in one linked list, right? Okay? But in my expected case, this 100 can be divided to, for example, 33 zeros, 33 ones, and 34 twos. Okay, how do I get 33, 33, 34? That is your 100 divided by the number of buckets. Okay, so this is your n, this is your m. You expect that. Okay, okay, so you expect that if your hash function is good, okay, if your hash function is very good, you can split this 100 evenly into each bucket. Okay, if your hash function is good, you can split this evenly. Okay, and hence each bucket will have n per m. Okay. If you want to ask me how to prove this, you can use pigeonhole principle. Okay? Something like that. But if your hash function is good, you will have n over m. But if your hash function sucks, right? If you happen that from x, you will always convert to x multiplied by 0. If your hash function is always like this, right? Then confirm all your 100 items will always go to this bucket, right? So in that case, whose fault is it? It's the fault of the hash function. Okay? So let's discuss about this hash function. Hashing will only be good as long as you have a good hash function. Okay, this part is very important. If your hash function is biased, right, then you will never achieve the O1 runtime for hashing. Okay, and what is the characteristic of a good hash function? Anyone? Is this not? I think it's not ready. Fast.
These solutions.
Okay, there's a principle. There's a principle. There's a specific term for this. What do we classify as a good hash function? 4 letters.
Simple.
Yeah, Suha, okay? So what is Suha? SUHA is simple uniform hashing assumption. It's SUHA, not SUGA, okay, for those who like K-pop. Okay, so it's SUHA. This is an assumption that if your hash function is good, you are going to map every key equally likely to every bucket. Okay, so for example, if you have an integers of 1 to 100, right? If you do modulo 3, okay, then you have like equal chance of, for example, going to 1, going to 2, going to 3, okay? So in this case, if your hash function will have equally likely possibility of mapping every key to like one bucket, then in that case, that will follow the simple uniform hashing assumption. Under this scheme, right, under the SUHA scheme, the probability of a key being present in a bucket is 1 over m, where m is the number of buckets. Hence, if we have n items, right, if they are mapped equally 1 over m, then we will have like each bucket will contain like at most n over m, those kind of stuff. Okay, so combining, if we are doing chaining, then we are having something like this. Okay, this part is for chaining. That will be O1 plus n over m. That will give you your O1. Okay, for open addressing is also similar. That's the alpha, which will also return us also O1. Okay, so back again. Hashing runtime is O1 if and only if it follows the simple uniform hashing assumption. Okay, if it doesn't follow this, if your hash function is biased, then cannot be O1. Okay, so far any questions? Questions? No? Okay. And by now you should appreciate that if there's no collisions, that is already a happy hash table. Okay? Okay, so that is about it for this quick lecture recap. Now we are going to move on to the tutorial questions. Question 1 is very easy. Okay, try hashing these items 42, 24, 18, 36, and so on and so forth with the hash function h of x is equal to x modulo 7. Okay, everyone knows the modulo function, right? We are taking the remainder if divided by 7. Okay, each row in the table corresponds to the bucket of hx. Okay, so we have like quite a number of people here, like about 15 people. Then we have, I think, 16 items. Oh, wait, sorry, 12 items. Okay, so maybe one by one from front. Okay, from Samia snake around. Okay, Samia. For 42, what is the result modulo 7?
0.
Okay, that will be 0. Alex, 24?
3.
3, okay. Share you?
4.
4, okay. Snake around. 36 modulo 7.
1 mod 7.
Okay, 1 mod 7. Liam? 3, okay.
0.
Andrew? 0. Okay, so 42 modulo 7 is 0, and so on and so forth. So we are going to put 42 in which bucket? In bucket 0. 24 in bucket 3, and so on and so forth. Okay, so this is the first half. Second half, Ferdi?
5.
5, okay. So 47 modulo 7 is 5. Then, Jia Kai? 3, okay. 1. 60 divided by 7 is 56. Remainder 4, right? So that will give you the 4, okay? Then 27? Ife? 6, okay. Then Wang Che? 32 modulo 7? 4, okay. And finally, Kevin?
0.
Yeah, 0, okay. So putting everything in a bucket, we will have this table. Okay, easy? Easy? Okay, easy. Now, second question. What if instead of a linked list, we use an AVL tree to store the items in a bucket? What are the advantages and disadvantages of such a solution? Okay. There are a lot of aspects to cover here, so maybe if you can give like your ideas. One person, one advantage, one disadvantage, cannot.
In fact, is this AVL tree, like, if you look through the whole thing, it's not in.
Okay, AVL tree, if you look through the whole thing, then that will give you ON for lookup, right? ON lookup.
Oh, yeah, there we go.
Log n, right? Sorry, log n lookup, right?
Yeah.
In the worst case, you will have log n def. What about linked list?
Okay.
In the worst case, there will be ON, yes. Any more?
Disadvantage is that you have to somehow maintain the AVL tree.
Disadvantage, you have to maintain the AVL tree, correct? So that part, if you're going to insert, right? If you're going to insert, then you need rebalancing in the AVL, right? So insert will be O log n for AVL. But linked list will be
Oh, fun.
O1. Okay, because for linked list, you just need to modify the next pointer of the last element. Okay? Any more?
For AVL, you need the objects to be comparable.
Sorry?
You need the objects to be comparable.
Object should be comparable, yes, for AVL. Whereas for linked list, since we are not doing sorted things, then you can just easily append. Okay, what else? So far we are talking about the runtime, right? How about the space? I think runtime is quite covered already. What about space?
Same.
Space is the same, okay. Is there any difference between AVL and linked list for the space? I think a bit covered in last tutorial also.
Is it the overhead before the links between
Linked list is-
Hey, there's an overhead. Who has more overhead? Linked list has more overhead than AVL?
I think
Or AVL has more overhead?
AVL.
Okay, let's do a quick poll. Who says it's AVL has more overhead? Who says linked list has more overhead? Okay, why linked list? Okay, maybe why AVL first?
Because every single node has 2 pointers. You have to point to 2 different nodes. While linked list, you just point to the next.
English just point to the next, okay.
And just 1 pointer.
How about show you why linked list?
I'm not so sure. I just chose.
Not sure, but linked list might seem more overhead. Okay. Okay, so for space itself, yeah, correct. For AVL, you might need 2 pointers. One is pointing to your left subtree, one more is pointing to your right subtree. So each node will contain 2 pointers. As compared to your linked list, right? Your node should only just contain the next pointer lah. Except if you want to contain the head or tail, then that's your choice. But minimally, it should just contain the next node. Okay? So for linked list, yes, you will only need 1 pointer. Hence, more overhead will be taken for AVL. Although it will still be the same order of growth, but for AVL, there's more overhead lah. Okay? It's like, for example, one will be like, say, 10 kilobytes, the other one will be like 15 kilobytes, something like that. Okay? Now, what else? Okay, oh, is this all? Any more to add? I think there's one more aspect missing, but okay, let's discuss. So, yeah, for runtime, for searching, right? Of course, it will be clear that for linked list, you might need to search through everything if the element is at the last element, right? Okay, so for example, if I want to search for 4, then I need to traverse everything. Whereas as compared to AVL, my worst case search would just be log n. However, if you are doing insert, then for linked list, that will just be O1 because you just need to append. But for AVL, you have to search through where you need to insert, and then you need to rebalance. So for AVL, that will take O log n for rebalancing and inserting. Okay. Now, what about space? Although it says the same about ON, but then you will have more overhead because this is how you're going to structure your classes, right? Your linked list node will contain your value and also the next pointer. Whereas for AVL, you need to keep your value, the left pointer, the right pointer, and also whether it is currently balanced or not. Okay, if you recall on how we implement AVL in like the past tutorials, we will keep a 2 bits balance factor, right? Everyone remember this? One is the -1, then the other one is +1 or 0, right? So that balance factor will also take part in your AVL tree node. Okay? This is used for checking whether you need rebalancing or not. If you do not put this, later on it will be very costly when you do the rebalance part. Okay? Now, one more thing that is not covered is, in the perspective of a coder, AVL tree is much harder to implement, right? Okay, much complex because you might need to put the logic for the rebuilding. So I think you guys have done through PS4, PS5, have suffered through how to make a tree on your own, right? If you do linked list, you just need to put like the pointers and that's it. For AVL, this is you lah, okay? But of course, there's one more perspective. As a grader, I am also dying lah from reading your code. Okay? So that is AVL trees. Any questions? Although there's a quick tip here, regarding the runtime, if your hash function chosen is very good, right? Then in both cases, your expected time should be equal. Because just now we discussed about the worst case time, right? The log n and n, right? But if your hash function is good enough, that is under the uniform hashing assumption, then in that case, the expected time should be identical. Okay? And one bonus fact, in fact, the hash map of Java is using red black trees. It uses a linked list from this bucket to red black trees. There's like a specific change of implementation. I forgot in which version. But now it's using red black. Red black is similar to like the KD, so one red, then another level for the black, then another level for red, those kind of stuff. Okay? So far, any questions? No? Okay. Now, we know that hash tables will store pairs of key to value, right? Okay? So once we have like a key, then we are going to take the hash, keep that inside the array of that index, right? The value. So the question here is it sufficient to just store the value, or do we need to store the entire key value pair? Or another way to rewrite this, do we need to store the key inside the hash table? Okay, maybe 10 seconds to think first. Do we need to store the key in the hash table, or do we need to just store the value? It's okay already. Okay, so who says we need to store the key value pair? The key also. Okay, who says we only need to store the value? 1, 2, okay. Okay, maybe from the value first. Why value? Why value is sufficient?
The key can be kind of like the index.
The key can be kind of the index, yeah? Makes sense?
So we just store the values.
Okay, so you can just store the values because why do you need to store the key again if it's already in the index, right? Okay, show you?
Well, I thought the key was already in the hash table.
Yeah, so same reasoning, because the key is already the index, then why do you need to store again? Okay. How about the others? Maybe 2 people who want to suggest, okay?
Yeah, I think as we saw with the collisions thing, because multiple keys can map to the same slot, right? So that's why I think we also need to store the keys along with the values.
Okay, so you're suggesting because the key can be mapped to multiple keys can be mapped into one slot,
One
so we
slot,
need to
yeah.
store the key. Okay. How about Ying Qian?
Yeah, basically the same point.
Basically the same point lah.
If you put, if you don't store the key and you have 2 different values that catch the same table, when you go searching for them, you don't know which is which.
Okay.
You can't find the proper value.
Okay, yeah. So far I accept all ideas here. Okay, your ideas is also correct. Because in fact, if you are just simply keeping the key value pair directly, right, if from the key, I find the key index, then I keep the value, then of course, why do we need to store the key value pair again, right? However, in a general term, okay, your hash table may have different keys mapped into the same slot. So it comes back to how big is your hash table and what is your hash function. If your hash function is doing something like modulo, right, then 21 and 15 modulo 3, right, they will map to the same bucket. So we don't know which one is which. Okay, so both of these are correct. However, in terms of saying more general one, then we might need to store the key value pair. So here's a quick example. Suppose I have 8a and 15a. Okay, key value. So 8, for example, my function here is I will take the key, I modulo 7. Okay, so 8 modulo 7 is 1, 15 modulo 7 is also 1. Okay, so this will map to one value in my hash table, that is 8. Okay, now the question is 22 modulo 7 is also 1, right? Does that mean 22a is also in the hash table? No, right? Because the previous one is only 8 and 15. But it happens that because it maps to the same one, doesn't mean that it will also be inside the hash table. Okay. Then another problem is, for example, if I have something like this, 8 and 15, but A and B, so something like this, 1A, B. Now if I have like 15, does it map to A or B? We don't know. Okay, so in this case, it is necessary to store both the key and the value. So it comes to the possibility of whether it can map to the same bucket or not. If it is uniquely identified, for example, if it's just an integer of 1 to 256, then your hash table is also from 1 to 256. Then of course you don't need to store the key, it's okay. As long as the key is mapped directly unique. Okay? But in the case that most of the times our hash table, right, it should be less than the domain itself, because or else we will have a storage explosion. We cannot store everything, right? So in that case, there's a possibility it can map to the same bucket, hence we need to store the key. Okay? So yeah, both ideas are correct. Any questions? Questions? Okay. No questions, we are going to move on to I think the past question in our tutorials. So given n items in no particular order, but this time possibly with duplicates. Okay? Sorry, this time possibly with duplicates. You want to find the missing number. For example, if we are counting from 1, right? Then we want to find which number is missing from that array. Okay? Or output all present if all values from 1 to n were present in the input. So we want to find the missing number. The first missing number, sorry. So if 2 missing numbers, that means like which one is less. Okay? How can we solve this problem? Everyone reads the tutorial problem, right? I think there's an example given because I'm lazy to write. Yeah. So like there's an example given, the 3, 5 something, and then like you want to find the missing element. So just find which, from counting from 1, 2, 3, then you see that 6 is the missing element, so you get 6, something like that. So how can we solve this? Of course, the most efficient implementation. Don't suggest to me an O(n) squared algorithm. Okay, ideas.
I was thinking you can put into a hash map.
Okay.
Hash map take up the keys into an array, and then we can do like some sort of binary search.
Okay, so we can do hash map. Then from the keys we put the array. Then do a binary search. How do you do the binary search?
So let's say we go into half, and let's say when we reach the middle is 4, but the index is like, let's say 3. I think that means something on the left is missing.
But research on the buckets.
Binary search on the buckets, yeah. Which side to recurse? Which side do you recurse? So something like, for example, here. Okay. Say now my bucket is something like 1 here. Then suppose I have like 2 counts here, okay? Then bucket 2, there's only 1 element. Bucket 3 empty. Bucket 4, I have like 1 element. Then bucket 5 empty. Then bucket 6, 1. Then bucket 7 also 1. Okay. So that means I have the mid value. That's 4, right? Because 7 divided by 2, math law, that will give me 4, right? Okay. Is it 4? 7 divided by 2? 3, yeah. Sorry. Okay forget this. The middle element is 4, right? Suppose okay. The middle element is 4. Then I see that okay, 4 has an element. Then which side do I recurse? How to recurse later? I see that 4 has an element, okay, then I need to recurse.
Just use the right side.
Right side?
Why?
But isn't everything here 1 to 6?
No, like 3 and 5.
So 3 is empty, 5 is empty.
What about we just linear search?
Yeah.
Anyway.
Actually, yeah. The best way is to do linear search. Because why? Even if you do like this binary search, right? Okay? You don't know where to recurse. Okay, then if you do binary search, you have to recurse on both sides. Worst case is you do the okay, yeah. That part the worst case will be ON lah later lah, because you have to recurse, something like that lah. I think even worse I think it should be like ON lah, I think. Yeah. Okay. So in this case, yep, you're correct. We are going to put a hash map, of course. Okay, because from this point onwards, if you can't do something, just use hash map lah. Okay, most of the problems in this tutorial will be done using hash map. Okay, so we are going to use a hash set. Okay, just another variant of hash map lah, to store all the values that we have seen in the array. Okay. Then using this hash set, we are going to ignore duplicates because we don't need to actually check for if they have duplicates or not, because we are concerned on whether the value is there in the first place or not. Okay, and finally, we will go through the hash set to check if each number was present starting from 1. Okay, so since the hash set will support O1 operation, okay, O1 lookup, okay, hence we can count everything from 1, 2, 3 all the way to n, right? Which one is not present? Okay, so from 1 you check if it's present, go to 2, check if it's present, go to 3, check if it's present. So O1 operation for lookup multiply by, at the worst case, you are going to check n times. So there will be ON, plus to insert everything in the hash set also ON. So that will give us the ON runtime and ON space. It should be okay, right? Okay, so hash map, no need to do the binary search because we don't know which part to recurse, so that doesn't help the runtime. But we can just count everything from 1, 2, 3 to n. And ON is already very good. Okay, so by this point, you can realize that why are we using a hash map? Hashing is done in order to reduce your runtime, but at the cost of space. Okay, so hash map is actually a trade-off between space and time. Okay, by reducing the time, you are using space to accommodate for that faster time. Okay, so by using much space, you will reduce time. That is what hash map is. From something that is supposed to be done in n log n time, we reduce to n at the cost of ON space. Okay, so far any questions? No? Okay. No, then there's a bonus question here. Can we do the same thing using just O1 space? It's an in-place algorithm, so we are not doing any additional space, but we can still use the same array in front.
I mean, yeah. Very naive solution is just to have like a counter that keeps track of the first number that is the number you're trying to track for, and then you simply just go through an array. Every time you encounter like this number, you increment it by 1. Okay, and then you keep doing it. So ON squared solution.
Okay, yeah, that's a very nice solution. Yeah, thank you very much. Though with that solution, we can also just do a quick sort n log n, then that will be much faster. Okay, any other solutions?
So for example, we start at the very first index of the array, so it's an 8. So we swap the A to the index 8 of the array, and then we get another number, right?
Yep.
And then we swap that to the index of that array, right?
Yep.
And then we do this until one or two things happen. Either we get index 1, the index that is correct, then we can move on, or the array that we are about to go to. So for example, let's say I have 2 as my first index, but then index 2 is already 2. Then there's no point in swapping. Then we can just move on to the next. Next element, and then we continue and repeat for the regular array.
Yep, exactly, that's the solution. Thank you very much, Ping Jian. Okay, so everyone get the solution? No? Okay, so yeah, that is actually the recommended solution. So suppose I will have a 1 index array. Sorry for violating this convention, but I think it's easier to see. So index 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I have these elements. Okay, so first of all, I see an 8. Then what do? I swap, right? So I swap 8 with the element at index 8, right? So in that case, I see 8. At index 8 is 4. So I swap 8 with 4. Okay, so I take 8. I go to index 8, I swap. Now in my index 1, my number is 4. Then I will repeat the same thing. Okay, I go to index 4. I see that this is 3. So I do a swap. Okay, so I swap this. Now I am sure that this 8 is correct in its index. This 4 is correct in its index. Okay. Then I see 3. Okay. Can I swap 3 with index 3? Can I swap?
No.
If I swap, like, it will be a cycle later. Okay? So in this case, I see that, 3 here is equal to 3. So in this case, I can just leave it alone. Okay? Once I leave this alone, I will move on to the next element. So the first one, I leave it untouched first. Okay? I go to 2, then I will swap with index 5. Okay? Then 2 here is correct, 5 is correct, then I move on to here. I swap with index 1 all the way until I terminate my algorithm later. So you will see that although this part, right, it is badly sorted, right? This one is not a sorting algorithm. However, if you see the front part, if the element is present in the first place, since we are traversing through everything, right, then it should be already in its own place. Okay, because of that non-cyclic part, if it's already in its place, then we don't touch. If it's not in the place, then we will swap. So that will ensure that every element will get a chance to be in its own place. Except that if it's duplicate, then there's no guarantee that it's in its own place, the 3 and 2. Okay? So yeah, this algorithm will work. Then how do we know which element is missing?
Check linearly.
Yeah, we are going to check linearly. Okay? So 1, 2, 3, 4, 5 is correct in its own index. But at index 6, your element is 3. So what is the missing element? 6. Okay, then we return the index. So this algorithm has a specific name that is called cuckoo hashing. Okay, so you can check Wikipedia page here on how cuckoo hashing works out. Okay, but I'm surprised no one actually suggested the idea of. I think last tutorial we discussed about adding everything one by one, right? Okay. Anyone knows why it doesn't work? Adding the integers together because of duplicates. Okay, because the array here has duplicates, that's why we cannot do the addition then divide lah. Except that it is a unique array, in that case we can do addition lah. But still, if the missing element is more than 1, then we cannot do so. Okay? So far, any questions? Questions? Okay. If no questions, we are going to move on. Now the third and the fourth question is quite fun because we are going to design a data structure. Okay? So now we are going to design a data structure called randomized set that has the following operations. Randomized set initializes the data structure. Then insert will insert an element, insert an item to the set if not present. Remove will remove the item if present. And finally get random, which returns a random element from the current set of elements. Now the key catch here is all operations must work in expected O1 time. Okay, so this part is the challenge. Any ideas? This part is a challenge, the expected O1 time. So. I guess.
Array.
Use an array, okay. How do you use an array? Use a okay, use a hash map. Okay, that's another solution using a hash map. Get in? Use 2 hash maps, okay. 2 hash maps, okay. What else? Those who just say the answer, I will ask you how to implement, okay? Okay. Array, how to implement array?
Insert, you just insert to the end of the array, like the last element.
Okay.
Of the array. And then remove, you just oh, I think yeah, cannot.
ON this one. ON. Okay. Single hash map. Anyone single hash map just now? I think a lot of people said. Okay, Lian. Single hash map.
I think randomize is just put some random number. Random number can be so you just insert random numbers. Insert is O1, remove is O1. Get random, you just generate a random number. Just a random number and then use that as a key and retrieve from hash map which is O1.
Okay, so this get random part is as long as you get the keys right, you can retrieve the element later. Okay. How do you get the keys here?
You just
Do another random number generate. Sorry?
you just do a random number,
Uh-uh.
and then you do a random number, and you use that as the index and just retrieve.
Okay, so this one, as long as you have like, how do I say? As long as you know what's the size of the hash table, then you can do this random number generator, right? Okay, this one works if your random number generator itself, your set is almost fully filled lah, or at least half filled, those kind of stuff. Okay, because in that case, the probability of you actually having an element is quite high. Okay, but in the case that the probability is not really that high, right? Then you might need to do another random lah. But in that case, we'll still get the O1 also lah. Okay. But any other solution? Okay, the two hash map solution.
Wait, sorry. For the random, what happened if the structure didn't have any element?
Okay, what happened if the data structure doesn't have any element? Good question. I think it should throw an exception for this. Because how are you supposed to get a random item if you don't have an item in the first place?
Yeah, but if you only have one element, right? The randomized part is like you random until it get the exact value.
Yeah.
So it's something like and
Yeah, so this is the main problem. If it happens that your hash table, right, you initialize it with, like, for example, length 100, right, then you only keep one element, right, the probability of getting one element correct is 1 over 100. Okay, so that, in that case, right, if you do not keep track of whatever random elements that are there, right, it might do an infinite loop also, like if your random number generator sucks. Okay, so in that case, yeah, thank you very much for showing. This is the main concern with just keeping one hash map. Okay. As I mentioned, this part expected O1 correct. As long as your hash map is necessarily full, okay, in that case that where there's actually a specific type of problem called, I think it's called a birthday problem, if you all heard. Okay, that for example in a group of how many people, right, what's the probability that two people have the same birthday? Okay, I think that's like about 50%. Okay, I think that's the birthday problem, you can search for it. So as long as there's a specific minimum number of things inside your hash map, right, then in that case your probability might be quite high, more than 50% of getting. But if it is very sparse, okay, if your hash map contains like 100 elements, you're going to get random from 100 elements, right? The probability of getting it correct only 1 over 100. Repeat another one, also 1 over 100, right? There might be an infinite loop of not getting even. Okay, so that's the main problem of using the hash map only. So two hash map solution.
Then your first table is going to be a integer to your value hash map, and then
Okay.
the second table is going to be value to integer.
The second table is what table? Sorry.
Your first one is integer to value,
Okay.
and then your second one is value to integer.
Value to value to integer.
It's
Yes.
the same thing, but like so insertion is quite straightforward. Like you just insert, like let's say the first element you insert 0 value, and then to the other table you insert value with 0 as key and value pairs.
Okay.
And then you increment your count. Then deletion is, if you are deleting the last element, it's straightforward, so you just delete for both tables. If you are not deleting the last element, you edit, like, okay, you look up the last element using your count variable. You edit your current value to, okay, you edit your deleted value, the value ID, into that last variable, into that last value, and then you delete the last value from both tables. Right?
Yep.
Then for get random, you just randomize a number between 1 and the count, and then you just return from the m value.
Okay, yep, this will work. So by keeping another hash map, in this case we are going to like some sort of memorize which of the things inside our hash map actually has some values. Okay, so in this case, you can randomize whatever data is stored inside. Then in that case, you can get whatever is being kept inside. Okay, yeah, this works. This is actually the improved version of the single hash map version. Okay, yep, this will work. Great solution. Ideas or suggestions? Okay. Any other solutions? Yep. Thank you very much, Kevin, for this. Yeah, very nice. Other solutions. In fact, the recommended version is similar to this, but it's not this. What if I tell you that we can actually combine this with the array implementation? How does it work? Let's see. So suppose now, instead of using just a hash table or using just an array, we can now keep both an array and a hash table. Okay? How do we do so? Upon initialization of randomized set, we are going to create this empty hash table, and we are also going to create your array of size n. Okay? So in this case, we will append the value to this array. For example, I insert 15, then I put inside my array 15. Then in this case, I will add my size, and also I will add it to my hash table. That means I'm storing that the key is 15, the value is 1. Okay? Then I continue adding my value to my array here. So 20, add it, increment the size, then I add the value and the size to the hash table. Okay? Why do we need to keep the size? Keeping the size here is important for, as what Kevin mentioned, this acts similar to like the second hash map. Okay? So once you want to remove, okay, sorry. So to get random is easy. From this size, I will call a random integer. Okay, so sorry. Oops. Okay, so get random is simple. From the size of your array here, I will call a random integer. So random from 0 to 2, right? Okay, from 0 to 2 minus 1, that is from 0 to 1. Then I will just get the array's value here. Okay, so from the random integer, I will see at that index what is my value, then I return that. Okay, so the important part here is your array here will be stored as that much. This array will guarantee you that one of the elements here will always be in the randomized set. So there's no probability involved in this case. Okay, the only probability is getting the random number that's although deterministic, but still a different probability to get the random. Okay, so the only probability involved is to get which is the index, but no longer on whether is the value present or not. Okay, so that's why we need to keep the array. Okay, and for remove, we are going to check in the hash table if there's actually a value present. If there's actually a value present here, we are going to remove it from the array. We are going to remove this. Okay, but how to remove? If I'm just going to remove this and shift everything, that will take on, right? So the way to do this is I will swap it to the back of my array. Then I will then I will decrement the size. So I will move this to the back of my array, change that element to null, then decrease the size. That is how I remove something from an array. Okay? But of course, the second hash map also works for this case, yes. Because it acts similar. And the space should not be much different. Okay? Any questions? So this is a quick recap. Initialize the array, that's for a randomized set. Insert, you are going to insert the value to the array, or the second hash map also. Okay? Then for remove, you check the hash table if the value is present. If it is present, you are going to retrieve the location, swap to the last, set it as null, and reduce the size. Okay? And finally get random, it should be simple. Okay? So far, any questions? Questions? Oopsie, what happened? Okay. If no questions, then I guess it's time for us to take a quick break before we move on to the remaining 2 questions. Okay. If y'all want to go to toilet or drink, feel free to do so. Oh, okay. This one?
복수하자.
Baby shark, da 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 da. Baby shark, do 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 do. Baby shark, do 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 do. Baby shark, do 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 do. Baby shark, mommy shark, do 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 do. Mommy shark, do 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 do. Mommy.
like USB from 2.0 to 3.0. Now, instead of implementing everything that has to be done in O1, we are going to insert in O log n, delete in O log n. Of course, if you can do O1, it will be best lah. Okay, look up in O1, but finding successor and predecessor in O1 time. So this part is a bit difficult. That is why we are raising the time complexity here to O log n lah. Okay. Any ideas? Successor and predecessor, good question. You can think of it like the element before, element after, something like that.
Let's try AVL tree and the hash set.
Okay, AVL tree and a hash set. How is it?
So the AVL tree is just we just store all the values that we want to input. And the hash map, the key value pair, the values will just be the values, but the keys will be the nodes of the AVL tree.
Key will be the nodes of the AVL tree. Then the value is the
Key is
values.
something that represents the nodes of the AVL tree.
Okay.
Then insert, we will just update the AVL tree accordingly. Then
So suppose I do something like this. Maybe something like this can be easier to see. Okay, if I insert say 15, what do I do?
you create a node in the AVL tree first. You convert this node into a key value pair into that, and then store it in the hash map.
Okay, so in this case the key is this.
The key will be something representing the node. I'm not too sure what it can be. So
Okay, maybe anyone has ideas what can be the key and the value if you agree with that
but the
implementation.
value I can just store it.
So this will be like the map bar. The key, the value.
Then the value is like whatever.
Okay, the key can be 15. I think 15 can be easier as the key because it's an integer, right? So I can just convert that to the index 15, so something like this. Then I have 15 here. What about the value? Successor, predecessor, then what?
We put the memory address of the
Memory. Okay, that's a high term there. Okay, memory address of the node, or in short, just the pointer to the node. Okay, it's referencing the node. Okay, so in this case, it will switch a bit. The key can be the value, and the value is a pointer to the node. Okay, pointer to node. Okay. Just know who raised hand? Caitlin, that's it. Yeah.
Successor and predecessor.
Okay, successor and predecessor. How to store? If you want to store the successor predecessor in the value, how do you do so?
Store it in a pair or something.
In a pair.
Some data structure that allows you to look out maybe one.
Okay, so
You pre-compute when you do insertions.
we keep the successor predecessor. Okay. Pre-compute. Okay.
Like in this case, there isn't any kind of because it's one thing in the tree. Like you insert another one. Then after insertion, you look out successors and predecessors using the initial tree.
Okay, so after insertion, you look the successor predecessor, then you put it here. Okay.
And then you update no. So because now let's say you insert 21 with your next line, right?
Okay.
So after inserting 21, you know that its predecessor is 15.
Yeah.
So you would store 21 and then 15 and nothing as its predecessor successor. And then you will go to 15th century and update its successor as 21.
Okay, so basically I update everything from this node to the root lah. The successor predecessor. Easy.
Just not to the root.
Because you 15 will be updated, right? Oh, okay.
You update its predecessor and its successor.
Oh, okay.
You only need to update two of them.
Oh yeah. So you will be updating this 15, updating 21. Okay. Yeah. Okay. So you'll be updating the 15 and 21. Okay.
And then deletion is symmetrical.
Deletion is symmetrical.
Like you just look up its successor, predecessor, map them to each other, and then delete the node.
So actually for the previous one, the successor, predecessor, right, I'm concerned with this part. For example, if you have like, say in this case there will be like 8, then there will be like say another 14 here. Then in this case the predecessor of 15 is, would it be 8 or 14?
And when you insert, like what was the last inserted one?
Last inserted one is 14.
So when you insert 14, then it would find 14's predecessors and successors, right? And then you update 8 and 15.
Okay, so this part until I reach the root updater.
Hash table, you have to update 14, 8 and 15. Like you insert
okay.
14 and then update 8 and 15.
Okay, so update everything up to the root. Okay.
No, only 3 elements.
3 elements only.
You only update its predecessor and its successor. There's no other elements you need.
Okay, I'll keep that information. Okay, update these 3 elements. Okay. Then how about the delete part?
What?
The delete? How the delete data?
Delete, you just, okay, then if you want to delete 14,
Okay, delete 14.
you check its, so you find out that successor is 15 and predecessor is 8. You edit 8 and 15 so that 15 is 8's successor and 8 is 15's predecessor. And then you delete 14. On both the tree and the hash table.
Okay, yep. Okay. And lookup
Hash table.
Okay, yep. This will work. Yes. So actually, for delete part, right, I would suggest you can just do the deletion in the AVL first. Then afterwards, whichever is affected, then you update directly to the hash table afterwards. Because in that case, right, you can just trace the path and that's just log n also. So that's covered in the O log n time also. Okay? Because you might need rebalancing also later. Because this one is AVL, right? So in that case, any affected one, then you just need to do an update later. Okay? So yeah, this will work. Any other solutions? Others. Or other possible implementations here. Okay, so this part is we are keeping the successor predecessor inside the value, right? What if instead of the successor predecessor, we only keep the pointer to the node? Okay, let's discuss this first alternative one. If it just keeps a pointer to the node, does it work? Okay, so how do I keep the predecessor successor in the node?
You just store it as an additional field. Then every time you insert, you update the node until it's root to check for the successor and predecessor. That's what I've done. And delete is in a single function, so that's what I've done. And loop up we just do loop up we just do hash table up. And to find the successor and predecessor, you do the hash table, and because it's a pointer directly to the current instance, you can just access the field and you will watch.
Yeah, this will work. So one way is to keep the predecessor and successor in your hash table. The other way is to keep it also inside your tree on its own. Okay, so by keeping it inside the tree, we are doing what we call the tree augmentation. We are modifying the node so that it will keep a pointer to the predecessor, pointer to the successor, okay, or the value of predecessor successor also works. Okay, so these are 2 alternative implementations. So I'll be discussing the question. Yay. Basic questions. Can this be done just by using a hash table? No, why no? Can this be done by just using a hash table? The hash table, right? Oh, shit. Okay, hash table, right? Insert is O1, delete is O1, lookup is O1. Can, right? Why can't we use a hash table? Successor, predecessor, I can just expect O1 also, right? Just move back, move front. What's wrong with the hash table? Yep. So if the hash table here, right? If my hash table is very sparse, I have empty keys here, right? Then to actually find, I need to search one by one. It's very tiring. Okay, so to find the exact immediate predecessor successor, right? It might be very long if it's a sparse data. If something like this, it will not work. So which is why we cannot use a hash table directly because of the successor and predecessor. Okay, so can we use just a pure AVL tree? without hash table, can we use AVL tree? This part is easier. No, because of your lookup. Okay, this part clearly cannot. Okay, so if I compare AVL and hash table, this is some sort of AVL tree. Predecessor successor is O log n without augmenting. Okay, and here predecessor is ON. So I can take like whichever ones I want. I see that the predecessor here might be faster as compared to my hash table, but hash table supports O1 lookup. So to get the best of both worlds, then I will follow your ideas. That is to implement both an AVL tree and also a hash table. So this AVL tree, we are doing some modifications or augmentation so that the node will store a predecessor and also successor. Okay? And finally the hash table, we are going to store the pointer to the AVL tree node. Or the method suggested by Kedwin also can. If you keep the predecessor and successor also in the hash table, that will also work. Okay? So both ways will work. However, do note that if you are storing it inside the hash table also, right, then you will need to create another data structure also for this, the pair part or something. Then that might take some time also. Okay, some additional overhead. Okay, because you will be making new objects again. As compared to here, right, you just need to modify the initial object, just add 2 fields. Although it is similar, but then the other one you might need to allocate memory also. Okay. So in this case, the working will be similar to the previous ones that I illustrated. Okay. So far, any questions? No? Okay. No questions then. Last question for the day. Yep, today running quite fast. So coupon chaos. This part is quite fun. Mr. I'm not sure where it's Noodle, not Noodle, has some coupons that he wishes to spend at his favorite cafe, but there are different types of coupons. So there are T distinct coupon types, and he can have any number of each type. A total of N coupons. Okay, so $5, $5, $10, $20 can also. Okay. He wishes to use one coupon at a day, but he wishes to use his coupons in ascending order. So if I have like 5, 10, 5, 10, 20, 20, 20, I want to use the 5 first, all the way up to the 10s, then the 20s. Okay? Noda wishes to build a calendar that will state which coupon he will be using. The list of coupons will be given in an array, and of course it is unsorted, because if it's sorted, then you are no longer used as a programmer. Okay? So something like 520, 520, something here. The number of distinct coupons is your T, that is 3. But the number of coupons present is 8. Okay? So here the output provided will be like, for example, 3, 3, 5, 5, 20, 20, 20. Since the menu in the cafe is not very diverse, not many different types of coupons. Hence, we can say that T is much smaller than your N. Okay? Something like quite often also in Singapore, right, your coupon cannot be like, say, $17 coupon is very rare. Mostly like 5, 10, 20, 50 directly. Okay? So in this case, we can safely assume T is much smaller than N. Give as efficient an algorithm as you can to build his calendar. I think this question is not hard, right? Three-way partition quicksort, how do you do so? Okay, yeah, you're going to just do the three-way partition, keep every duplicates inside, then you recurse. Afterwards, you will have the sorted order, right? Sorted ascending order with duplicates. Yep, that will work. Other solutions?
Counting sort.
Counting sort, okay. So you're going to count, keep, and then return, okay. That will also work. Then, Mingchen?
Hash table plus array.
Hash table plus array? How to do the hash table plus array?
First you iterate through that input, and then you put all of it into a hash table. Like, so the hash table is a frequency table of the values. So like, let's say I find 5, then I will increase the value of 5 by 1 in my hash table.
Okay.
So and then I see a second 5, it will become 5 is linked to 2. Then once I'm done with that, I get all the keys in the hash table. That's usually a method for that. Then I sort those keys, so T log T, in ascending order, and then for each of the values in that new like sorted array of keys, I get the value in the hash table, and then I put that amount of coupons I have into my answer array.
Yep, that will also work. So you put a hash map, then array for the keys, then you sort the keys, get back the elements from the hash map, right? So the hash map acts similar to like the counting sort part. Okay, you keep the count, the frequency, then you get back. Yep, that is similar to the counting sort. Okay, any others? In fact, counting sort is very similar to the hash map also, because you are keeping the very large array, right? That is basically a hash table. If you recall, right? You keep a very large array, that's your hash table actually. Any other implementations? No? Oh, okay. Okay, so if you realize the question is just simply a sorting problem but with duplicates, which is why Li Yan's solution will work the quick sort with three-way partitioning. Okay, so let me discuss. There are three recommended solutions here. First one is using an AVL tree, but in this case we are going to augment the AVL tree node to store a count. Okay, so for example 520, 520, 320, 320, I will insert 5, count 1. I will insert 20, count plus 1. Then I insert 5, the count of 5 here I will add 1, right? So count will become 2. Then 20 I will add the count, 3 I will add it to the AVL, then 20 I add the count, 3 add the count, 20 add the count also. Okay, so in this case I will have an AVL tree of just the distinct items, the distinct coupons, but now I will keep the count also. Okay, so from here I can just do, to get the final array, what do I do in an AVL tree? In order? Pre-order? Which one? I think I did something wrong. In order, right? Should be in order, right? Yeah. Forget this, but I did something wrong. Should be in order, yes. forget this. Should be in order, yes, because my solution is also in order. Okay, I forget the terms. But basically, you do an in order traversal. I will edit this later. Okay, you will be going down until you reach the leftmost subtree. Then once you terminate, you are going to edit. Okay, so I go to 3, I add 3. Then I go back to 5. Now I go to my middle element, right? So now I will process here, so 5. Then afterwards, I go to the right subtree. Then the 20. Okay, forget this, it's in order. Okay, I mixed up the terms. Okay, so 3, 3, 5, 5, 20, 20, 20, 20. That is one way. Okay, so we do the in order traversal with the AVL tree. Hence, we will get the array. Second way is by VN. We do a quick sort with three-way partitioning. Okay, to do the quick sort, I think this one you should be able to do this. You keep a 5 here, then as a pivot, for example, the first element as pivot for illustration purposes. Then I will get something like this. And for a distinct, only 3 elements, right? So just one partition will be done. So this will be the sorted array. Or finally, what's the last method? Last method? Yeah, counting sort. Always a hash table, okay? That's the third method. So in this case, yep, it will be correct. We are going to store a hash table to store the count of each key and also a list to store all the keys that we found. Okay, so in this case, I will keep the array. I create an empty hash table. I create an empty list or array can also. So I add 5, but I check the hash table first if it is present. If it's not present, I add the count as 1, and I will add it to my list of keys. Okay, or you can also do the keys method from the hash tables support. That will also be possible. Then you go to 20, check the hash table, then add the count, add to the list. Then 5, it is there, so I will just increment the count. 20 is also there, I increment the count. 3 it's not there, so I add the count as 1. Then I include in my list. 20 is there, increment the count, increment. Okay. Now once it's done, this list of only 3 elements, I will need to sort this. And sorting this, I will get 3, 5, 20. Then I will pop out the elements from the hash table, one by one from the start, 3, 5, 20. Okay. So from 3, I retrieve the count. 3 here, it has only 2 elements, right? So that will be 3, 3. Then go to 5. 5 has 2 elements, so 5, 5. And finally 20 has 4 elements, so there will be 20, 20, 20. This is how the hash table works with the additional list. Okay, this list can also be obtained by the keys the hash table.keys, something like that. Okay, that will also work. So this will return us the sorted elements. Now, before we end the class, What about the runtime? Okay. How about AVL3? Where's the runtime for AVL3 implementation? N log n? N log n? Anyone says n log n too? Who says n log n for AVL3? 1, 2, 3. N log t? Who says n log t? Okay, more people say n log t. Okay. So, the number of levels is only determined by the distinct items. If you only have 3 distinct items, then the level will be log 2, log 3 lah. So they'll give you like 1 level, 2 levels lah. Okay. So log t levels, and also you're performing n insertions. So the time it takes, right, is the time to insert and also time to actually do the in order traversal. To insert, you have n items to be inserted in log t levels lah. So in that case, there will be on log t plus the time to traverse. There will be on because you will ot. Because you have to traverse through every single node. Okay, this part should be t, sorry. So on log t plus t, that will give you your on log t because it's more dominant. Since we know that n will be much greater than t. Okay. How about quicksort with 3-way partitioning? Okay, yeah, there will be n log t. So n elements with t distinct keys, then that will give you n partition times log t times you are going to recurse, right? So that will give you n log t. With the case that you are doing the random pivot lah. Okay, so to ensure that your pivot will divide them equally. Okay. Now what about the hash table plus array implementation? Just now I think Ping Chen mentioned already. N plus t log t. Anyone agrees with n plus t log t? 1, 2. Who says it's not n plus t log t? Can suggest. We will keep a hash table. We keep an array. Every time we want to add, we add things to the hash table. If it's not in the hash table, then we also add to the array. Then we sort the array. Then we pop 1 by 1 from the hash table. Okay. Who says it's n plus t log t? 1, 2, 3, 4, 5. Okay. Of course, Ping Chen mentioned n plus t log t, right? Of course, Ping Chen agrees, right? Okay. Yifei, Somya?
Shouldn't be n plus t.
N plus t? How is it n plus t? Not sure? Yifei? No idea. I know. Okay. So, the number of keys, okay, number of keys in your hash table, there will only be t. Okay, because you are going to have only t buckets later. Actually, a lot of buckets, but then the buckets that you use is only t, right? Okay? And you have n items to be inserted. So the time it takes, right, is time to insert, plus time to sort, plus time to actually return the sorted value. Okay? So time to insert, plus time to sort, plus time to return the sorted value, which I didn't include. Okay? So time to insert, since to insert things in a hash table and an array is just O1, so O1 times n elements, that will give you On. Time to sort is t log t. Why t log t? Because your array that you are sorting has only t elements. So you are only sorting t elements, and the fastest way you can just quick sort or merge sort. That will give you your t log t. Plus the time to actually generate back the array, right? It's just OT. Because now you have the sorted elements. For each element, you look up the value from the hash map, then you return how many. So that will be just OT. Okay? So On plus OT log t plus OT, that will give you your On plus t log t. Okay? But here's the catch. Since we know that t will be much smaller than n, then this will be approximately similar to On. Because if you're very large n, right, say 1 million n, but only like say 5 or 10 t's, right, then in that case it will be similar to On, approximately equal to On. Okay, any questions? Nope. Okay, so that will be it for this tutorial. It's quite fast, I know. So the conclusion is, from the 5 problems we've seen in the tutorial, if you say that you want to use a hash table, 90% expected time you will get it right lah, okay? And this is actually the very important topic for technical interviews, open and online assessments lah, okay? So by mastering this topic, you are 1 step ahead from becoming a real programmer lah, okay? Because it's actually a very common thing that we do lah. A lot of optimization problems can be solved using hash map, because it trades your storage for extra efficiency in your time. Okay, trade your storage so that your runtime from n log n reduced to on, which is very good already. Okay, so that'll be it for today's tutorial. Thank you very much for coming. All the best for problem set 6 and PIUs for the remaining of the semester. Thank you guys. Today quite fast.